So this is example number 1 on linear fracture mechanics. In this particular example, what we're going to do is we're going to consider a flat panel. And this panel, this particular panel has a tensile load. Let me change the colors here quick. Has a tensile load of 50 kilonewtons. It's made of this titanium alloy material, and has a crack propagated right in the center. Okay, so it's propagated in the center, and it says the total length of the panel is 400. So half of the length of the panel will be 200. This says the total width of the panel is 100. That means that B is equal to 50, half of this. The thickness is equal to 5 millimeters. So this is given, all this stuff is given in the problem. Okay. So the first question you are asked for is find the valid Kc. Okay, what Kc do I use in the problem? From this particular table that I provided, but you can use in your any other table, you can see that the material property that we are working is with the one that last bottom here. And the units that we are working with are megapascals and meters. So therefore, the two values I'm going to use are these two values. Okay, so I know from the problem that KIC, plane strain KIC, is 34 megapascal square root of M. And I also know my sigma yield, that's 325 megapascals. Okay, this comes from the table again. So to see if this is valid, I need to find my transition crack length that's given by 2.5 multiplied by KIC divided by sigma yield squared. That would give me 2.5. 34 divided by 325 squared, and that gives you 0.0275 meters, or it would be 27.5 millimeters. Okay, and you can see in the problem then, your problem is actually saying that the thickness given in the problem is less than transition crack length. Since it's less than your transition crack length, because this was 5 millimeters, is less than 27.5 millimeters. Okay, then that means that my Kc that I need to use in my problem would be Kc multiplied by 1.224 times Ts divided by T squared. And you replace all the values in here. 34 square root of 1 plus 0.4224. This is 27.5. This is 5 squared. So therefore, the Kc in the problem would be 94.8 megapascal square root of M. And what you can see in the problem is I have a lot more available to use than if I had just used my plane strain value that I got from the table. That was 34 megapascal square root of M. So this is, you can see immediately, there's a big advantage of doing it like this, right? To using this value over this. You will avoid having to bulk up your structure unnecessarily. The second question your problem is asking is, what is the transition crack length? Okay. So the transition crack length, I put length between quotes because you have to look at the problem itself, right? Look at if you go back to the figure that we taught, what I told you in the books, this is a figure that we'll be using. It says 2 times A, and we are using only A in our equations. So it's half the crack length, okay? So that means the transition crack length AT in this particular example represents half the crack length. Okay? So in your problem, then, this is the equation that we use. Okay? So when we find the crack length, your crack length was defined as follows. One over pi KIC sigma yield squared, which gives you 1 over pi 34 divided by 325 squared. So your transition crack length is 3.48 millimeters. Okay? So let's move on. The second problem, the third question that's asking is, if the total crack length, if the total crack length is 20 millimeters, will it fracture? Will it initiate fracture? Okay, so we know that we're working 2 times A is 20, so really A is equal to 10. Okay, so we know that A transition was 3.48 millimeters, right? This is 10 millimeters. So what we are really working with is on this area, because A is bigger than AT. So we are working with fracture. Okay, so that means it's fracture brittle failure. And in our problem, we will assume throughout the problem that we have a design factor. The problem doesn't say that, but remember, we always have to add something. So I'm going to assume that this is 1.2. Okay, so let me just show you that yield is not an issue, right? Okay, it's not an issue because your A is actually bigger than this. But just to show you, look what happens. Sigma yield, sigma YY, sorry, true sigma YY would be 1.2, your design factor, divided by 2 times B minus A times T. And if I replace all these values here, 50,000 and this value, you find that this is equal to 125 megapascals, which will give you multiplied by 1.2 megapascals. Okay, so your problem would be the maximum that's available to my actually required. That would be 325 divided by 125 multiplied by 1.2, and that will give you 2.17, which is bigger than 1 and is safe, and there will be no yield initiation. Okay, so this is to show you don't have to do it, but just to show you that it's actually our assumption was correct. Okay, so since I'm working with fracture, so that means that for the fracture criteria, what I need to do is I need to work with my factor safety equal to what is actually available to what I really need of my fracture toughness. Okay, so I'm going to move on to the next slide, next page, and I'm going to write all this. KC over KI And this I already know from the problem because I calculated that in item 1. This was megapascal square root of m. Okay, and I know that my mode 1 fracture toughness is beta sigma yy divided by pi times a. This is no crack. Okay, so in other words, the value of this will be sigma yy is equal to design factor PA divided by area, design factor PA divided by 2 times BT is equal to why 2 times BT. Again, if I was to come back here, I'm looking for the value where there is no crack. So if I go back to my problem, this is the problem I had. So I'm looking for, you see, this one has a crack all the way through. Just remember, it's all the way through crack. So I am saying what happens, I don't have no crack. So my total area without the crack would be 2 times B times T. Okay? So if I plug all these values here, then 1.2, 50,000, the value of B, remember you have to be consistent in your units. This will give you 120 megapascals. Okay, this has to be megapascals, by the way. So, and then from the problem, I know that this is 10. The only thing I have to miss is this value. This comes from tables. Or charts. And so we go back to this problem right here, next chart, and we see that for in this particular problem, D is equal to B. Why? Because this is a center plate, so the values are the same. A is equal to 10. B is equal to 50. So from here, A over B is equal to 0.20. D over B is equal to 1 because it's actually from here is equal to 1. So if I use 0.20 here, this value, and I go here and I find this value approximately, I just happen to know the exact value. So the value is 1.04. I got it from equations, but you can, just guess estimate from here. This is 1.1. This is half of it. So it's a little bit below half of that. Get that value. Okay. So now that we have that value, I can go and calculate fracture toughness for this particular problem is Ki is equal to beta times sigma times pi times A. And that would give you 1.04 multiplied by 120 square root of pi times 10. And that gives you 22.12 megapascals square root of meters. Your factor of safety then would be your Kc divided by Ki is equal to 94.8 divided by 22.12, which will give you 2.29. And once again, you can see that this is actually bigger than 1, so we can say the problem is completely safe. Now, as a contrast, as a parenthesis, what would happen if I was actually using KIC instead of KC, then this is what would have happened in your problem. This would have been 34, 22.12 is equal to 1.54 is bigger than 1, which is also safe. But you can see immediately how I have less cushion here than I have cushion there, right? Here I have a lot more to work with. Many times we end up bulking up the structure unnecessarily, and so we can avoid that by doing this. Okay. Part C of the problem says what happens if total crack is 60 millimeters. If that was the case, then from here A is equal to 30. Okay, and once again, you can see that A is bigger than A transition. So it is initiation of brittle fracture. So if that was the case, then the same thing. This is beta. I need beta first. I need sigma, and I need pi a. I know this. This is given from the problem in study. This I need to find from charts. We'll find it in a minute. And this right here is when I have no crack present. Then actually your problem, it will be identically the same as before. Why? Because I haven't changed my problem. I haven't changed my dimensions. I haven't changed my load. So therefore it will still be 120 megapascals. Let's go and find beta from the charts. So you come to the chart and you see that same thing holds. D over B is equal to 1. A over B is equal to 30 divided by 50. That gives you 0.60. So now you are somewhere here, and you just go all the way up here, go up here, and then this is 1, go more or less here, find this value. I just happen to know the exact value, 1.31, but you could have said 1.3. That would have been completely perfect and acceptable in the problem. So let's just go ahead and replace all the values now. You have Ki is equal to beta times sigma times pi times A. You replace all these values here. You find this 47.46 megapascals. So your factor of safety, then this problem will be Kc divided by Ki. That gives you 94.8 divided by 47.46. This is equal to 1.98. This is bigger than 1, so we are safe. Let's see what would have happened if I had used a plane strain assumption. Is plane stress, so this will be correct. However, if I had done that, you could have seen that the value that you would get, this is 34 divided by 47.46, gives you 0.71, is less than 1, so it fails. It failed. So this is a very good example. This is a good example in a point where what happens if I actually end up bulking up the structure unnecessarily when my structure is feeling has this much cushion, but I limit the cushion to plane strain to plane strain assumption. You have to be very careful for that when you do this type of analysis. Okay. The last question in the problem says, for what load PC will initiate brittle fracture if the critical crack length is 30 millimeters. So you know 2 times A is equal to 30. AC is equal to 15. Okay, and you know that AC is bigger than transition length, so it's going to fracture. And note that I'm using here Ki. When I want to find loads P, I want to be conservative. So I want to use this value instead of the value of Kc. Okay, I want to initiate fracture, onset of failure. So onset of fracture, onset of failure is equal to 1. Okay, so the problem basically says the critical fracture toughness of mode 1 has to equal to my required mode 1. Okay, so let me write this down, that when finding PC, use Ki. C, not Kc. Okay, so so let's go ahead and replace all the values here and see what happens. KIC is equal to beta times this value, PAC, and we know that this value would be, sigma would be this value, PC times A. This is your design factor times the critical load that I'm looking for, 2 times B times T. This will be 1.2 times PC divided by 2 times 0.05. Multiply 0.005. So if you resolve this, this gives you 0.0024 PC. The units will be megapascals, the way we derived it. So your AC over B will be 0.3, and if you go to the charts, you find that beta is equal to 1.051. Again, I got that using the exact solution equations. They're given in my notes, by the way, if you want to mess around with them, but they are not needed. You don't need that in this course. So this is going to equal to beta times sigma times pi times A. This is 34 is equal to 1.051. This is 0.0024 PC, square root of pi times 15. If I solve for PC, I find that my total PC is 62.1 kilonewtons. This is the maximum load my structure can possibly have before it starts failing for a total crack length of 30 inches. So this concludes example number 1 for linear fracture mechanics.